How's it going, Carter?
Good. How are you?
Not too bad. See, Tanika, did you get your stuff done earlier today?
Yes, I had did it yesterday.
Oh, okay, good. That's right. That was yesterday call. I got another call today, and it wasn't for you. Obviously, it was for someone else, but I was just remembering yours now. Uh, been in and out of bed for 2 days straight. Kind of forget which day's what. All right, looks like we got a pretty good number already, so I'm going to go ahead and get started since we just got here at 5:20 anyways. So I thought I'd start off by stating Maxwell's equations. Remember last time I did tell you you were expected to be able to identify and use Maxwell's equations, including Ampere's equation, or Ampere's correction, excuse me, Ampere's law with Maxwell's correction. Sorry. But if you remember yesterday or last time when I tried to show it to you, I said I couldn't necessarily remember. I got it right, except I said a partial derivative instead of a regular derivative, but that's not too big of a deal. So, anyways, I still decided to go ahead and give you the list of Maxwell's equations, explain them a little bit more, as well as giving you them in a slightly different form, which is the form that more serious work is usually done with. We can do some interesting stuff, obviously, as you've seen from this course with Maxwell's equations. But when you really use the differential equations as opposed to the integral equations, it's a lot more user friendly, even though there's some nature to differential equations that makes them virtually impossible, and then solving them, other than in the most beautiful symmetric type cases, is really hard. But sometimes you just have to write computer code to get it. So, anyways, let me go ahead and turn on my iPad sharing so that you guys can see it. And I just sent out an email to my 202 class, and when this class is over, I'm going to be sending out another one to you folks, giving you all a list of office hours that I'm going to have tomorrow, Saturday, and Sunday, as well as a list of all the times that, why is this not doing it? As well as a list of all the times that you can actually take your exam. Oh, there it is, finally. So I sent that out to 202, but I didn't have enough time to do it before logging to your class, so you haven't received it yet, but you will. So keep an eye on your emails, and in that email, I tell you to keep an eye on your emails over the weekend. I also tell you to keep an eye on your my YouTube channel over the weekend, because if I make any new videos, they're probably to help you guys with your finals, so you really, really don't want to miss anything I might make up. I thought I'd muted that. Let's see real quick. Oh, I did. It just alarms. It does that. Okay, so here's Maxwell's equations. The left side is Maxwell's equations in integral form. Basically, you have Gauss's law, and y'all are all familiar with that one. Really, to understand how I get from there to the differential form, I'll explain that in a second. But right now, just pay attention to the left column. So that's the closed integral over a surface of E dot dA is equal to Q enclosed over epsilon naught. Then there's Gauss's law for the magnetic field, and that's the closed integral of B dot dA over any surface is equal to 0. That one's often been interpreted as there are no magnetic monopoles. In other words, we've done a lot of experiments trying to make sure whether the right-hand side of that equation is 0, and so far we've got it to several decimal places, like 10 to the negative 20th or something like that. So we think the thing is at least as small as 10 to the negative 20th. It might be 10 to the negative 16th. I'm not really that sure. It's been a while since I looked into the research in that area. But basically, the fact that it seems to be 0 says that whenever you cut a bar magnet in half, it doesn't become a north pole and a south pole, but rather two bar magnets with a north and south pole in each one of them. And then if you cut those halves in half, it does it again. But eventually you get so small that the domains of magnetic alignment sort of fall apart, and it just becomes eventually not magnetized at all. So you're never going to cut it in half and get just a single north pole or just a single south pole. So that's the second law. That's called Gauss's law for magnetic fields. There's Faraday's law, which I wrote in the E parts, the red parts, because that's a different way we might have typed it, and also are seen it in the book. But also that in there is when there's more than one wire loop, then you have to put the in there because n is the number of wire loops. But basically, what it says is the induced EMF, which is that red E, is equal to negative n d phi b over dt, where phi b is the magnetic flux, the integral of b dot da. Okay. If you have only one coil of wire, then n is 1. You don't have to do anything. But also, if you wanted to use that to find the electric field, like we did with the magnetic field, that's causing for instance, changing magnetic flux or whatever, or creating that electromotive force, you could, in principle, treat the left-hand side like we do the left-hand side of Ampere's law, and find the electric field. You'll see there's an example like that in your book, even though I'm not covering it. So just not covering it out of lack of time. So that was Faraday's law. And then below that is Ampere's law with Maxwell's correction. And basically that says the closed integral over a path or a line or a contour of B dot dl is equal to mu zero I enclosed. That's what we've worked with so far, but it also includes this term plus mu zero epsilon zero uh, times the time derivative of the electric flux. Now, uh, we can actually convert these two differential equations by using Gauss's theorem, which is also called the divergence theorem. That's why I wrote it down there. It just says the closed integral, meaning an integral over a closed surface of F dot dA, which is the flux of the field F, the vector field F, through the surface of any closed surface. So if you calculate the total flux coming out of any closed surface of the vector field F, you will get basically that's equal to the divergence of F from the volume of that uh, volume or surface. So remember, you had a closed surface that had a clear inside and outside. So when you're doing the left-hand side of Gauss's theorem, you're calculating the flux leaving that surface. And what it's saying should be common sense, specifically the divergence of that vector field F over the whole volume has to equal that. That's pretty much like saying, hey, if you tell me how many gallons per second you're losing of water in this tank, then I can tell you exactly how much water is coming through the hole in your tank, right? So that's literally the left-hand side would be an explanation of how much is coming through a hole in your tank, and the right-hand side would be how much is the water level decreasing inside the tank. Then there's Stokes' theorem, which you might want to call like a curl theorem, which is kind of weird, but basically imagine the right hand side first. In that case, what you're thinking is the right hand side of Stokes' theorem says the curl of the vector field F dotted over a surface. If you take that calculation, sort of a fluxy type calculation, then that over any surface, by the way, that is equal to the amount of flux that is multiplying by the arc length on the contour that surrounds that surface. So for instance, we're imagining not a closed surface on the right-hand side where it says the integral over A. We're just imagining a surface. It could be like last time I showed you Santa's bag. So we could imagine Santa's bag being the actual volume. It's got an open hole on the end, but basically if you calculate the divergence over the entire surface of that bag, then that's going to be equal to the integral of the field around the opening. So that one's a little less obvious to see, but when you work with it mathematically, it works a little more straightforward. But by using that and using things like the charge is equal to the integral of rho dq, and using things like I enclosed, the current enclosed, is equal to the integral of j dot dA. Using those expressions along with Gauss's law for the first, or excuse me, along with Gauss's theorem and divergence theorem for the first two equations, our Stokes theorem for the last two equations, we're able to come up with those four differential equations that you see there. So that's what Maxwell's equations are. Hopefully, that helps you a little bit at least appreciate it. And I will tell you that it's not unreasonable in an upper level class like a senior or junior level class, if you actually take electricity and magnetism, say in an engineering program, or electrodynamics or electricity and magnetism in a physics program at the junior senior level. A very common first test question would be state Maxwell's equations in integral form and state Maxwell's equations in differential form. Another one would be convert Gauss's law in integral form to Gauss's law in differential form, or vice versa. So those are all things that'll help you. Just knowing those equations, knowing that Stokes theorem and Green's theorem exist, and knowing sort of some ideas of what you do. That all those things are helpful. So helpful that Giancoli has put a derivation of these differential forms in the appendix of your textbook, so you can check that out there. Anybody have any questions on that? Okay, so again, this is way more stuff that you need to know. Like, I'm not going to ask you about, uh, the Stokes theorem and Gauss's theorem. I'm not going to ask you to memorize the differential forms of the Maxwell equations, but you are supposed to be able to identify, Gauss's law or Gauss's law for magnetic fields, or the fact that there's no magnetic monopoles, or Faraday's law or Ampere's law. Okay. So when we last spoke, I had just given you an example of the Biot-Savart law, and we used it to calculate the magnetic field around a long, infinitely long, straight current-carrying wire. And then rather than use it again, I jumped to using Ampere's law without the correction. The correction can be used, but we didn't need it at that point, so I just left it off. But we used an example, or we did an example of Ampere's law to calculate the magnetic field around an infinitely long current carrying wire, and showed that it was exactly the same result we got from the law of Biot-Savart. So now I wanted to go back to the law of Biot-Savart specifically so you can see how to solve one particular type of problem, and then there's like a billion of them that you could make up. So let's go ahead and get started with that. What I'm going to do is I am going to draw a wire, a current carrying wire, and I'm going to draw it in a weird way, but there's a reason for it. So what we're going to imagine is that there's a wire coming from the left-hand side, and then it makes a half circle, which the stupid computer program is going to make into a hyperbola or parabola or something, just to be mean. Okay, that kind of stinks. Let's get rid of that guy. Okay, and then I'm going to say it goes around. Let's say I'm making a circle roughly this big, so something like that, and then it goes on straight this way. Okay, this is enough for us to show exactly what I'm talking about, but in principle, I could go and do other things, but right now I think this is sufficient. Uh, I'm going to say the current is coming in from this side, and then it arcs around this way, and then it goes this way. And now I'm going to draw coordinate systems just for completeness, so that I can speak exactly about where we are, what we're doing, and all that good stuff. So here's the x-axis right here, and here's the y-axis right here. Of course, here's the negative x-axis, and here's the negative y-axis. So what we want to know here is what is the magnetic field at the origin if I is equal to 20.0 amps and R is equal to, let's say, 0.100 meters, so 10 centimeters. Okay. And this is the R. And of course, oh, excuse me, that's supposed to be a lowercase r. That's the R. This is negative R. And technically, I should have made this line black so we know exactly what we're talking about here. Same thing there. Okay. So that's our plan. Okay. What we're going to use is the law of Biot-Savart. So I'll say solution. We're going to use dB is equal to mu 0 I over 4 pi times dl cross rp minus r dl divided by the magnitude of rp minus r dl to the third power. Okay, so that's the equation we're using. That's the law of Biot-Savart. And we got to remember, of course, what those things are. DL is a differentially, or I should say infinitesimal, an infinitesimal vector parallel to the wire and pointing in the direction of the current. Now, that's literally the source of the magnetic field in this equation that we're using. Like, I literally mean there's a differential amount of electric magnetic field called dB, and it's purely the result of a little section of the wire called dl being multiplied by I. Okay, so that's what the dl is. I'll say RP points from, from, everybody hopefully knows that symbol. That's O for the origin. From the origin to the point P where we wish to know B. In other words, the point where we're asked to calculate the magnetic field, that is P. And in this case, the origin is P. So the vector from the origin to this to uh, to P in this case is the zero vector. And then we have R dl. This one points from the origin to dl. Okay. So with all that in mind, we should be able to go ahead and figure out what's going on. I'm going to say this right here is the point P. So we should all be on the same page with that. Now I'm going to go ahead and start calculating vectors. So there's several parts here. I'm going to break it up into, let's call this A, let's call this B, let's call this C, and let's call this D. Okay. Somebody just came in. There it is. So those are the points. And what we're going to do is first look at A to B. So A to B. At A to B, I'm going to make a little differential line element right here that has a vectorness associated with it. So maybe I'll draw it like this so y'all can see it as a vector. And that little thing is going to be dl. So in this case, I'm going to say dl is actually equal to, notice it is pointing in the positive I hat direction, and its length, since it's along the x-axis, its length can be called dx. So we're just going to say dx I hat. Okay, remember the dl has to be parallel to the wire, and it also has to be pointing the same direction as the current. So this one fits that bill. We're good on that. Now I need the point P, which we said is the origin, which we might also write as 0, 0, 0. We also need RDL, so I need a vector that points from the origin to DL. I think you could all see, I'll draw it right here real quickly. Let's see if I can get a different color. The vector would probably be right about there. Okay, and it's just a vector. Ooh, excuse me, it goes all the way back to here. It's just a vector that points to the tail of DL. So in that case, I'm going to say, and hopefully y'all can guess this beforehand. We had some success with, I think, Tanika and Carter and maybe even Giovanna too. I can't remember if she helped last time. But in this case, I want you to think about what it would be. Notice that the vector is parallel to the x-axis, so there's an obvious thing that you could use. And I'm going to use that now and just say it's negative x is the length, and then it points in the negative I hat direction. So that's what that vector is there. And the most important thing we can look at now is RP minus RDL, which should be equal to basically the RP vector is 0. Oops, I guess I should do that first, even though I already told you that. So let me go ahead and do that one just to be certain. So RP, I already told you what that would be, but it's the vector from the origin to the point P. So it's literally the 0 vector. Now we can say, oops, now we can say RP minus RDL is something we would like to calculate. And you can see pretty easily that RP being 0 just means we put a negative in front of the RDL. So that's in fact going to be positive X I hat. Okay. Now we can determine the most important part, which is that cross product in the integral. So DL cross RP minus RDL is just, we write down DL, that's going to be DX I hat. Now we're going to cross that with X I hat. Can anybody tell me what the cross product of X I hat is with DX I hat? Or can you tell me anything about those two vectors, for instance, that would help us figure out the cross product? Okay. Well, I'm going to remind you that a cross product's magnitude, like if you take the cross product A cross B, the magnitude is the magnitude of A times the magnitude of B times the sine of the angle between them. The angle between the I hat vector and the I hat vector is in fact 0. And when you take the sine of 0, you get 0. So this whole thing is going to be 0. And that means we get no contribution. Okay. Actually, I forgot the word no. That's suboptimal. Okay, so that's what happens with AB. I think you can all convince yourself that with CD, that's also going to happen. Anybody have any questions about how that could happen? So I'll write it right here. What I'll just do is I'll point out that DL, which I was doing this in purple, so I should do it in purple, that DL is going to be X I hat, and that RP is going to be the zero vector, that P is the origin, that RDL is going to be, this time it's actually going to be positive X I hat, like that. And therefore, DL cross RP minus RDL is equal to 0 again. So part C, D does not contribute to the magnetic field either. Okay. Now what I'm going to do is look at part B to C. So, oops, thought I had black. I'm going to say B to C. So what I'm going to do first is I'm going to draw a little vector right here. Oops. Let's take away that last part I just drew. Oh, man. Okay. Let's take away all that stuff that turned out really bad. There you go. So I'm going to do that right there. That vector is a vector from the origin to the point DL. That's my plan anyways. Okay. So this vector is in fact going to be R DL. And in fact, DL, I'll make purple this time. That's supposed to be tangent to the line right there at that spot, or tangent to the wire, if you will. And I put those wires in quotation marks because it turns out the wire obviously is not the big point. What's really the big point is there a current? So if you have a current, which could be a lightning bolt or anything, not necessarily something in a wire, then it's going to happen. So that's why I keep putting the word wire in quotation marks, or referring to it sort of funny. So what I'm going to do is I'm going to now take this purple vector and imagine it having moved over a little bit. This angle right here is an angle d theta, and this angle right here is theta. Okay, so I'm not necessarily trying to say this is the theta that we use in polar and cylindrical coordinates. I'm just saying, hey, I'm calling that theta, and I'm going to work with it accordingly. Okay. All right, so now that we have this, I can see some way of calculating what DL is. So this little green vector here, I should probably point that arrow in green, so I'll do that. So this little guy is the DL vector, and I'm going to tell you that DL is actually equal to R d theta. And that's just from our famous equation from trigonometry with S equals R times theta. So instead of the angle being theta, the angle is a differential angle, d theta. Therefore, the arc length is R times d theta. And since these are infinitesimals, then obviously this is a case where the arc length and the chord length are essentially the same. So I have that for the actual magnitude. And I will tell you that this is sort of in the negative I hat direction, or negative theta hat direction. So I could say like this, because I've been talking to you guys about theta hat and everything like that. But I can also uh, blow it up and show you exactly what negative theta hat is. Let me do that on this next page just for a second. So what I'm going to do is imagine this is R. This is supposed to be perpendicular to that. This is d theta. This little bit right here is supposed to be the arc, so that's what RD theta is. But you can see as small as theta gets, the length of DL and the length of the chord length should be really, really close to each other. So that is DL is equal to R d theta in the theta hat direction. And what do I mean by that? Well, it's actually in the negative theta hat direction, excuse me. Let me do that a little better. Okay, so I can work out what this direction is. It's not that big of a deal. Remember what we had here. This is my y-axis. This is my positive x-axis. This is the angle theta there. So if I put an axis on this little green vector, then that would be my x-axis. This would be my y-axis. And what we said was that this angle right here, well, actually, I should probably put that in purple, make it a little easier. I'll do dotted purple. That angle right there is theta. So this angle is 90 minus theta. So this angle is 90 minus 90 minus theta, which obviously is equal to theta. Okay. So now that I have that angle, I can figure out what the x and y components of DL are. Specifically, I know its length is RD theta. So I can now say that DL, let's just work this out. DL is equal to, I'm first going to take the magnitude of the hypotenuse here. So I'm picturing a right triangle. Let me picture it in red so we can see what's going on here. I'm picturing a right triangle that has these two components. And remember, this angle down here is theta. So I didn't have to make it that small. That's just how good I am. Sorry. Okay. So that's what we're looking at. Everybody see this is the right angle, just showing that it's a right triangle. And then this other part, which I don't know if I can do this in here. I'll do it good enough though. So this is the angle theta. And this is the right angle. So you can see that the y component points up and the x component points to the right. Okay. So now that you have that diagram in your mind, you can say that the x component is in fact pointing in the positive direction, and it'll be equal to the magnitude times the sine of theta. So this one's going to be r d theta sine theta I hat. And then the other one is actually going to be a positive component as well. And its length is going to be r d theta. And then that's going to be times cosine theta. And that would be in the j hat direction. Now, I don't know why I wrote that in red, but I'll go back to green. So we can now see that this is r times d theta, which is common to both of them, times sine theta I hat plus cosine theta j hat. Uh, and this theta isn't exactly the same theta that we're going to do. In fact, this theta is technically 180 minus theta. Or excuse me. Yeah, this theta is Yes, 180 minus theta. That would be a better egg. So if you did that, you would come back to getting this in the same form of RD theta. But the main thing is we just needed a vector representation of DL that we could take a cross product of. So I'm in a good spot now. I can just write that down. That's RD theta sine theta I hat plus cosine theta J hat. So I can now take this and write it as R d theta. That's the scalar part, remember. And then I'm going to have a sine theta I hat plus a cosine theta j hat. So in other words, when we go to do a cross product, I can pull out the RD theta and the sine theta in front and then let I hat cross with whatever's on the other side of the cross product. And then I can do the same thing for RD theta cosine theta and then let J hat cross. So now that we have all that worked out, we can continue. Now I need RDL. Now RDL is just the vector that points to it. We've already labeled it. That vector is going to be equal to R cosine theta, negative R cosine theta. Notice it's the x component of it where I drew it is actually negative, so that's why I put that there. So it's negative R cosine theta I hat plus R sine theta J hat. So that's what my RDL is going to be. And now all I need is P, which we've sort of worked that out already. We know that P is actually equal to the origin, which is equal to 0, 0, 0, of course. And then RP is just the 0 vector. So now we can work out what DL cross RP minus RDL is going to be. It's going to be, we know what our DL is. It's this nasty thing. So I'm going to call this just plain A. Just so I can write it a lot smaller. I'm going to put A right here. And DL, as we said, was R d theta sine theta I hat plus cosine theta. Now, you're going to see this just once, everybody. I mean, it would be ideal if you learned it, how to use it from me, but that's a little bit more than most instructors want their students to be able to do. I mean, they all want them to be able to do this, but they know it's usually not that doable. So this is something that takes a little while to practice, but what I'm going to give you at the very end is a final result that's true for all semicircles like this. And you can put any number of parts of a circle around an origin, long as they all have the same center of rotation, they'll just add up or subtract up depending on which way the currents are and that kind of thing. And all the radial lines, like the current coming in, the current coming out, all those are not going to contribute at all. So I'll give you a very simple formula. I'm just trying to explain to you how we're getting it a priori. So there's my DL. That's going to be crossed with RP minus RDL. We know that RP minus RDL is just, actually, I'll write it right here. RP minus RDL is just equal to negative of negative R cosine theta I hat plus R sine theta J hat. Okay, so you see what it's going to do is basically make it a positive R cosine theta I hat minus R sine theta J hat. Okay, now that looks horrible, admittedly. Okay, but it's not as bad as it seems. I'm going to break this up by using my FOIL method, basically. But notice if I'm just doing, let me get a red marker here. If I'm just wanting to do this guy, then it's got to hit the I hat first, and then it's got to hit the J hat. So that's what I'm going to be trying to do with this. And when the I hat hits the I hat, what we're going to get is all the little constants come out in front. So all the little scalar numbers come out in front. So I'm going to get R d theta. That becomes r squared because there's an r in front of the cosine theta over there too. That's sine theta. Oops. R d theta becomes r squared. Let me make this a little better. Becomes r. I left a space where I'm going to come back and put the r squared in a second. So it's going to be d theta sine theta. Now I got another r. Now I've got a cosine theta. Now I've done all the I hat scalars in front of it, and all I have left is I hat cross I hat, which hopefully y'all know what that is. I'm going to give you a little while to stew over it, and I'll come back and fill in under that bracket in a second. Uh, Now we're going to say plus. Now I'm going to let the I hat term hit the J hat term on the right. So again, I'm going to have R d theta sine theta, but this time I'm going to get a negative. So let me toss out this and make it a negative. I'm going to get a negative, and then I have a r, so that'll make that r squared, and then I have another sine theta, so that's going to be sine squared theta, and then that's going to be that looks like it. So I get I hat cross J hat. Notice they're in exactly the same order as they were. The I is on the left and the J is on the right. Again, I'll let you try to boil and figure out what the I hat cross J hat is. I hope y'all can do that. Uh, Now I'm going to do the J on the left and start crossing it with the things on the right. So I'll say plus again. This time I've got R d theta cosine theta. This is a lot of mess. Trust me, there would be a lot easier work to do, and you'd see all this and skip it all. I'm just trying to show you all the gory details so you know once and for all that it does work. So that's the R d theta cosine theta from the left-hand side of the cross product. We're doing the J hat now, and the J hat's going to hit the I hat on the right. So now I've got another R that becomes R squared. I've got another cosine theta, so that becomes cosine squared theta. And then it is J hat cross I hat. I'll put it in parentheses like that. And I'll put this there. And that's two of the terms. Now I've got two more as well because I've only done the I hat term. No, actually, I've done three terms, so I only got one more term left. Sorry. I did the I hat term in its entirety, and then I did the J hat term on the left, but just one of them. So now I'm going to put a plus for the J hat hitting the J hat. And now I'm going to get R d theta cosine theta again. But this time, when I get to the other side, again, I run into that negative. So I'm going to erase this positive and make it a subtraction like I did last time. And now I'm also going to realize that the r d theta cosine theta is being multiplied by r. So that makes that r squared times sine theta. So that makes that cosine theta theta sine theta. And then times j hat cross j hat. Okay. So has anybody figured out what I hat cross I hat is? Remember, the magnitude of a cross product is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. So what's the angle between I hat and I hat? Remember that 0. and the sine of 0 is 0, so this quantity is 0. Can anybody take a guess what j hat cross j hat would be?
Also 0.
Exactly. All right, now we're going to do I hat cross j hat. This is where, if you remember that Levy-Chevatov pseudotensor I told you about, might come in handy, because you know that one of the cases of the Levy-Chevatov tensor that was 1, 2, 3. Well, I've got 1 is the I hat, 2 is the j hat, so we'd expect I hat cross j hat to be k hat, and that's exactly what it is. And the j hat cross I hat turns out to be exactly the negative of k hat. So you can work with that a little bit. You can use the right hand rule. That's really all you need is the right hand rule, because you know the magnitude is going to be 1. But the main thing is you need the right hand rule to go I hat cross j hat and see where your thumb's pointing, or whichever way you choose to use it. Okay. So now we've worked out the numerator of that god awful integral. So now let's go back and finish the job. So b is equal to the integral of db, which is going to be mu 0 I over 4 pi times the integral. Now I've got to write these things, and you'll notice I have a negative k hat multiplied by positive r squared d theta cosine squared theta, and then I have a positive k hat multiplied by a negative r squared d theta sine squared theta. So in fact, these two are just basically both negative. So I'm going to pull the negative out in front here. And what I'm going to get is r squared d theta times sine squared theta plus cosine squared theta, like that, and then times k hat. So does everybody see that that's all that's left? And of course, sine squared plus cosine squared, I know everybody knows that one, is just 1. So what we're going to get is the integral of r squared, which is a constant. So this is going to become negative mu 0 I r squared k hat over 4 pi times the integral d theta from theta equals 0 to, in this case, it's pi. Okay. So I think you can see that the integral of d theta from 0 to pi is just pi. So we're ultimately going to get negative mu 0 I r squared over 4 k hat. And that's the whole answer. Okay. So that's kind of wild, right? That's the whole answer. But what I want you to understand is it's actually not that bad to understand. If this was a whole circle, what would the angle I integrated through be?
Would it
Anyone?
be 2 pi?
Yes, it'd be 2 pi. So if you had actually done a whole circle, that would suggest the whole circle would be, ignore the negative and the k hat stuff. You can make that out that that's the right hand rule speaking to you. But the magnitude would be mu 0 I r squared over 4 pi times 2 pi. So that's what we're trying to figure out here. Let me write down on the next page a more cogent understanding of what it is. And wait a second, how did my r squared get in the top? Oh, stupid me. Do y'all realize I completely forgot the denominator of my problem? Everything else out was working great except for the fact that the R squared was in the top. So that's where I went wrong, but everything else is good to go. Uh, Here's what I'm going to do to fix that. I'm sorry. I don't know what just happened, but here we are. Sorry, everybody. We're almost done this, so don't worry too bad. Uh, I don't want that. I'm going to circle this stuff and put it on the next page and then fix it because we've got everything we need. So this is copy, and you're going to see it's really not that big a deal what I left out, but I still need to explain it. So I'm going to put this line right here to separate it from there. And now I'm going to say paste. And really what happens here is quite a bit different. So that part right there was just fine. But what I forgot to do, and it probably was excited because I probably did it because I was so excited about getting the sine squared plus cosine squared. I don't normally do it this way. I actually use the theta hats and r hats, but if I use the theta hats and r hats, then it's sort of blinding you to what's going on. In this case, remember we had in the denominator of the formula was supposed to be RP minus RDL magnitude of that cubed. So RP minus RDL for B to C turned out to be just uh, basically R cosine theta I hat. Oh, so they're wanting the magnitude of that. And of course, the magnitude of that is just R. So overall, this would be R to the third power. Okay. So remember, I told you it wasn't that big a deal. That's why it's not that big a deal. The magnitude in the bottom is supposed to be the magnitude of the vector. Let me do a little sidebar in case nobody's seeing that. RDL, RP minus RDL is this guy, so I'll steal it. Copy, paste. Okay. So is that, which basically means the magnitude of this, the magnitude of RP minus RDL is equal to that negative is going to distribute, and I'm going to have positive R squared cosine squared theta plus that one's going to be a negative, so that's going to be negative R sine theta, but all that's going to be squared, so it'll come out just like the other one, and then you'll have that, so it will become the square root of R squared times cosine squared theta plus sine squared theta. And then you can notice that this, again, is just 1. So we just get the square root of R squared, which is just R. And then, of course, it's raised to the third power. So that's why I wrote R to the third power down there. So does that make sense to everyone? All right. So my answer down here is correct, but luckily, well, it's correct in the sense that I'm only off by a factor of R in the bottom. So this is supposed to be a R squared to bottom because did we have R squared on top or did we have R squared on the bottom? Oh, it should just be a 1 over R thing. Yeah, that's right. Okay, so what we had down here, I'm going to fix it by putting, let's say I put it in blue, just so you can have some coordination of remembering what was going on. And here it's going to be R cubed. You can see that this 3 will cancel out with this 2, leaving a 1 up there. So now in this case, I'm going to say this is gone, but we're going to have a single R in the bottom. And that means this part right here has the R squared being gone again. and the R is in the bottom. Okay. So that's what we got for a half circle. And that's the right answer, by the way. Okay. Your book does a similar one where it does a quarter circle and it instead gets 8R in the bottom. So it gets mu 0I over 8R. So what I was pointing out to you is let's go ahead and get rid of this part or just line it off so we know that we finished talking about that. What we were talking about on here is we've got for our result half circle. We got mu 0I over, what was our final formula? 4R. It was 4 pi R basically. And then that was times just plain pi. And of course, plus we have to use the right hand rule. Okay, that gets you the direction, in other words. So B for a whole circle is equal to mu 0 I over 4 pi R times 2 pi. Okay, so you can see what happens in this case. The 2 in the pi cancels out with the 4 in the pi, leaving a 2 in the bottom. And your ultimate result is, in fact, just mu 0I over 2R. So really, this is the formula you want to write down or memorize, because for a whole circle, it's going to be this. If it were half a circle, oddly enough, instead of multiplying by 2 pi, you were just supposed to multiply by pi. So what happened was you actually multiplied by an extra 2. So now you need to divide by a 2 and get a 4. Okay. So that's the way you can think of it. And that just works for any problems that look like this. Let me show you exactly what I mean. I could have a wire come in this way and then make a half circle or even a 3/4 circle if I really wanted. And then I could do this and do a different radius up to here and then do a different radius down to here and then go like this. And those two lines that are parallel are really on top of each other. And then I could ask for the magnetic field at this point right here. That's all you have to do, because you've got a formula here for one radius, that would be R1. Then you've got another radius here, that'd be R2, and then another radius here, that would be R3. And all you need for that one, again, assuming that the current's coming in this way, going around this way, that way, and that way. Using my right hand rule, I see the half circle is going to cause it into the board. So we'll say half R1 into board, our screen in this case. And then I've got a quarter R2. But notice if you use the right hand rule on that one, that's coming out of page. And then you also have a quarter at R3, and that one's also coming out of the page. So, oh, I said paste. I don't know what happened there. Out of the page. So if you look at it that way, then you can just say, okay, well, all I got to remember is it was mu 0I over 4 pi r times the angle theta. That's the formula we're using for B. And that's for any arc theta. Okay. When it's a full circle, then theta equals 2 pi. So I've got a half circle, and that means theta is going to be pi. So this one's going to give me mu 0 I over this is the half circle, so this one become, or this is, yeah, this is the whole half circle. So this one becomes, did we get a 4? Yeah, so that one becomes the 4r. And then I'll say that one's in what we'd call I'll just say in. And then these other guys are supposed to be out, but this one's a quarter circle. So you're going to have mu 0 I over r, but you're going to have, instead of a pi on the top, you're going to have a pi over 2 on the top with a 4 pi on the bottom. So that's going to make it over 8. And the same thing with this one's mu 0 I over 8r. So basically, but that's a different r, by the way. This one's R1, this one's R2, and this one's R3, even though I use big capital ones. But that's all you have to do for any kind of configuration like this, is you just repeatedly use mu 0 I over 4 pi r times theta. Okay? Anybody have any questions on that one? I'm just looking at time. All right. So I did mention, for instance, with Faraday's law, there actually comes the transformer equation, which basically says the voltage of the secondary divided by the voltage of the primary is equal to the number of turns of the secondary divided by the number of turns of the primary. The current formula is the same thing, except the ends are turned over. So it's the current of the secondary divided by the current of the primary is equal to the number of turns of the primary divided by the number of turns of the secondary. See how I flipped over that? And that should be expected, because power is equal to I times V. And with a transformer, the best you can hope for is the power in equal power out. You definitely can't have more. So you're shooting for I1 V1 equals I2 V2. If the new V2 is, meaning if it's higher, meaning that was a step up transformer, then you'd have V2 is actually equal like 4 V1. Well, that means I2 is going to have to be 1/4 I1. So yeah, you'd expect the I and the V to be related differently. So hopefully you'll look up the simple little problems like that. But this is mostly it, is this material right here with the Biot-Savart law and the Ampere's law. So I need to show you a couple more Ampere law examples. Anybody have any questions on this? Okay. Now, so notice, just in case no one actually got what the result would be, I'm going to say this result is mu 0 I over, all of these terms have a common factor of 4 in them. Some of them are 8, but some of them are 4. So I'm going to pull out the 4 as well. I'm going to say B equals, and I'm going to put a positive sign on it. Okay, it's positive because what we got before was a negative k hat direction, which is into the page. So I'm treating positive k hat as out of the page. So those 2 1/4 are going to be positive, and they should, I think, ultimately give you a better result. So I'm going to put them first. And what we have left from the R2 case is just 1 over 2 R2. Oops, I wrote squared. 1 over 2 R2 plus 1 over 2 R3, and then minus 1 over R1, and all that times K hat. So just in case anybody didn't necessarily understand everything I was saying about how to put those three terms there in the right hand corner together, that's what I mean. Uh, one direction is already decided to be positive, which is out of the page, and the other direction into the page is therefore negative. So I just made sure I stuck the negative one for the n on the very end after a negative sign, and it was mu 0 I over 4R1, but I just had mu 0 I over 4 out in front, so just putting the R1 in the bottom is all I needed, just like all I needed was 2R2 and 2R3 in the bottom for the other two terms. So any questions on that? I know I didn't close the loop on it, so I figured I better do that. All right, so let me refresh your memory again regarding using Ampere's law. So Ampere's law again, Ampere's law is the closed integral of b dot dl is equal to mu 0 I enclosed. Again, we're not using Maxwell's correction. If we were, of course, that would be plus mu 0 epsilon 0 d phi e over dt. But anyways, we're not using that. So what I want to attack is a solenoid problem. So a solenoid problem is, imagine a really tightly wound spring, like when you first buy a Slinky. You pull it out of the box and the loops are tight right up against each other. So that's what we're imagining as a solenoid, only instead of it being bare metal, we would have some cover over it, some kind of housing that's sufficiently thick and sufficiently non-conductive so that current is only going to flow down the helical path as opposed to through the sides of it. So I could represent that, if you will, by a series of wires coming with a current coming out of the page, dot, dot, dot. And then I could represent the bottom of that with a series of wires going into the page, currents that is going into the page, dot, 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 and then another one here. So what I'm going to do is make each of these currents coming out of the page, and each of these is a current going into the page. And I'll show you anatomically, three-dimensionally, what this looks like in a second, but I'm sure you can, I hope you can already guess it, but not everybody's able to do that. So what I am making the argument for is that this wire, for instance, right here, might have came from some distance away with a current coming out like this, and then it goes down, comes out of the page to us, makes a half circle loop, and then goes back into the page and enters this circle right here. Okay. And then this circle goes back behind the page and makes a half circle and comes over to there. And then again, this to this, and again, that to that. Everybody see what I'm talking about? Now, if you look at the magnetic fields near two such wires, I could do this right here and just make them look sort of spaced further apart. I'll do 3, in fact. And then down here, I'll do 3 as well, so we can see exactly what's going on. If I use my right-hand rule on each of these current carrying wires, I would see, in this case, I'd grab the wire with my thumb pointing out of the page at me and perpendicular to the page. So I look down and my fingers are in a counterclockwise circle like this. And if I do that for this other one to the right, I'm going to do this one in purple. What I'm going to get is right here, it points this way. And then right here, it points this way. And then right here, it points that way. And then right here, it points that way. So that's what that one does. And then, of course, the next one would go this way, this way, this way, and this way. Similarly, these are going to go around in a clockwise fashion. So this one's going to go this way, this way, this way, and this way. And then this guy is going to go this way, this way, this way, and this way. And again, this one's going to be that way, that way, that way, and that way. Now, does that make sense to everyone how those magnetic fields are going to orient themselves? What I need you to see is basically that B is approximately 0 in between these gaps, but also out here, because uh, you're not going to have all the magnetic fields from the top wires combining with the magnetic fields from the bottom wires, all except in the center. So over at the top, you're just getting contributions, negligible contributions from the bottom, but you're getting contributions from the top. And then below, you're going to get only contributions from the bottom with negligible contributions from the top. So the really strong magnetic fields are going to be right here, right through the center of the solenoid, okay? And all this would be weak magnetic field. Okay, so that's what we've got need to think about. This is B is approximately 0 in between the wires. You can see it's automatically canceling out, but out here it's just a matter of only one side, so it's not nearly as strong as the others. So this means all these areas out here have B equals 0. This again is for a solenoid. So I just want to point that out. And now I'm going to solve it for, oh, by the way, I never plugged those numbers in on the last one, but you can certainly do it if you'd like. Sorry about that. I was trying to rush to get to this. So now that I have the solenoid, I'm going to go ahead and write a solution. I'm going to say solution. And we're using Ampere's law, which says the closed integral of B dot dl is equal to mu 0 I enclosed. And I'm going to choose a very specific path. I'm going to choose a path consistent with the right-hand rule, because remember, on that right-hand side, if you integrate one way around the loop, and then you wrap your fingers around that loop so that they're going the same direction as the way you integrated around the loop, then your right hand thumb is pointing in the direction of what it would call a positive current. If it's going the other way, it's a negative current. So you got to keep track of that. What that means to me is I'm going to imagine boxing off this little section and making this my path. Okay, so we don't really know how many wires are in there, but what I'm going to say is this wire, this solenoid, carries a current I, is L long, and has N turns. Okay, so that's what we're using here. So if we looked at the density of lines, that would be density of turns is equal to lowercase n, which this looks really reasonably stacked neatly. So that should be the total number of turns divided by the total length there. Okay, so I'm going to use that as my density of turns, and I'm going to say that this distance from here to here is a lowercase l. Okay. I'm also, notice if I integrate around this in a counterclockwise direction like this, then the right-hand rule suggests that a positive current would come out of the middle, out of the page, which is exactly what those currents are doing. So now I'm in a spot where I can go ahead and solve this. So I'm going to write in left-hand side. I've chosen my path, but I've got to hypothesize what my magnetic field is. So my hypothesis is B is equal to B of, let's say B of, I don't know, Y times I hat only in coils. In other words, it's zero everywhere else, but I'm going to say it's approximately zero everywhere else, and it's B as a function of Y down the middle, and the Y is your distance away. So, for instance, we might do this like this, put that to be our x-axis, and put this to be our y-axis like that. So now you can see B should only depend on the distance y maybe that you are from the center. We're going to see if that pans out that way. All right. So now I'm going to say left-hand side. Oops, that should still be green. Closed integral B dot dl is equal to, I'm going to first say the integral over the left of B approximately 0 dot dl plus the integral of B of y I hat dot dl is going to be dx I hat as well, and that's over the bottom, so we'll call that B for bottom, plus the integral over the right of, again, 0. Now remember that one's 0 because once you get to the loops out here, all this is approximately 0. But for this little part and this little part, the magnetic field is this way, and the dl vectors are this way. So that perpendicular dot product makes it 0. So that's why this is 0, because the dot product for a magnetic field here and a dl here is 0. And then out here, it's all 0. And then the magnetic field here and here with the dl here is also 0. So that's why that's actually equaling 0. dl plus we've got one more term, and that's the top, so the integral over the top, and that one's super 0, so that's 0 dot dl, and that one's because it's just weak the whole time, right? So now that we got that, we can say that the left-hand side is in fact going to be equal to, since we're on a line of constant y, the b of y can come back. Actually, it could depend on x too, so I probably should have written it as b of y or b of x or b of y and x, but either way, it doesn't matter too much. We're definitely not changing that. Now we've got the integral. Oh, man. Now we've got the integral of dx I hat dot I hat, which, remember, this isn't the cross product, this is the dot product, so this is just 1, and the integral dx from x equals 0 to x equals L is obviously just L, so our answer is B of y times lowercase l. The right-hand side is a little easier to make sense of in this case, now that I've explained that the density is, but it's supposed to be mu 0 I enclosed. And if it's a length L, then the number of wires is equal to the line density times L. So that'll give you the number of wires that are there. and I still have my mu zero out in front, and now I have the I going through it. So that's the left-hand side, or right-hand side. Now if I set left-hand side equal to right-hand side, then we're going to have B of Y times L is equal to mu zero N times L times I. You can see that the L's cancel out. And in fact, there's no function of Y. So using our hypothesis, we come up with the magnetic field is just mu zero times N times I, which, well, I'll go ahead and say in the I hat direction. And I'll say that that's also equal to mu zero N I over L I hat. And that's for a solenoid. Okay. You can look up the toroid. That's actually that's a little easier. It turns out to just be mu zero N times I over 2 pi R, where R is the radius of the toroid. A toroid is basically when you take a solenoid that's really long and you bend it into a circle so it makes a donut. Once you have that, then the radius, the sort of mean radius of the toroid is the R that happens in the bottom. So you get mu zero N times I over, well, let me write it here. Toroid. Spelling I don't know about. B is supposed to be mu zero N I over 2 pi R. And the magnetic field actually goes around, so it's probably best to say it's in the theta hat direction with a right-hand rule accompanying it. So anyways, that's the other formula. You're obviously free to go. Make sure you chat me your first and last names if you haven't done so already. I'm going to wait for the last person to leave in case anybody has any questions. Do please pay attention to your emails and maybe subscribe to my YouTube channel just long enough to get through these exams, because if I post something, I really want y'all to know that I posted it so you can check it out in case it's helpful for you on the exams. Have a good one.
Hi, Professor. I did have a quick question.
Yes, ma'am.
Is it still possible to take any of the practice tests I've missed?
No, that's the whole purpose of them is the to get you to take them before the test so that you can get better on the test. So yeah,
Gotcha.
I don't let you do that after the fact. Sorry
That's
about
okay.
that.
That's
But
okay.
you
Thought
still
I'd
have
ask.
that wonderful opportunity to bring up your face-to-face test by turning in your redo.
Yes. Thank you.
No problem. Have a good one. I'm not
You too.
saying your grade was bad, by the way. I'm just
No, I know. You're fine.
say that.
Have a good one.
You too, Gabriel.
Hi, Professor. Quick question.
Yeah, go for it, Micah.
I just wanted to make sure that you got the text from my supervisor.
Yes, I did. That was let me double check, bro. Uh this is yeah, I thought that. Wait a second. This one didn't have a name. Let me see who it was.
Should be from Mr. Washington.
Gotcha. Do you know the last four? Or at least the last three?
Let me look it up. We have a work catalog.
Because I've been sick, I've got 40 text messages here. So I'm looking.
It's a
Oh,
three two
Washington. Yeah, I
six three.
found him. Yeah, I got you. Yeah,
Yeah.
yes, I got his. Gotcha. So,
Yeah.
did y'all take that already? Because I don't recall getting this in time to. I clearly didn't respond to give him. Are you going to take it today or tonight or anything? Or you
Well,
can't?
I wouldn't be able to take it. I wouldn't have been able to take it earlier. I do go in for an operation tonight. Um,
That's
um,
rough, buddy. Well, don't worry about
well,
that. I mean, you need to
it's
take care of your operation
it's
stuff.
well, no, that's kind of what I was planning it around.
Right.
Yeah, because like that way I'll actually be with him.
Gotcha.
Yeah. And he could set that time aside for me.
Gotcha. So
Um,
you can do it like just before or right after or some time thereafter when you're not on.
yeah,
Okay.
sometime, yeah, so definitely sometime before 12. And I just know I couldn't do earlier because like I mean I know you have to set that stuff up with the proctor and everything,
Yeah.
and then they
He
have to
did.
type the stuff in for me.
He sent me this at 11 this morning, but that was actually when I was on the road, so I completely missed it until now.
I
But
see.
I'll go ahead and send him the questionnaire, and I'll send him the password that he'll need, so you can go ahead and do that. And I will also allow. Is it tonight that's going to happen, or is it tomorrow that's going to happen?
I'm gonna get with him tonight and
Okay.
see if he still has that time set aside for me.
Okay.
Um, if not, I will inform you on via text
Okay.
while
What
I'm
I'll
there.
do is I'll open it up for you through Saturday,
Okay,
just in case, and uh, that way you can do it, and I'll have everything sent to him now.
sounds great. Sounds great.
Thanks.
Like,
Sorry for dropping the ball on that, Micah.
no, you're absolutely fine. I hope you feel better.
Thank you. I appreciate that.
Yep.
Anybody else have any questions?
I do, Professor.
Yes, go for it, Evelyn.
Okay, so I sent you a text. You said you were gonna fix it, but I don't know if I know you were sick, so I don't think you had time. But for the online test, I
Uh-huh.
did attempt it 3 times since I thought it was an error issue on my side, and it's
Right.
still not allowing me to take it.
Oh, so the online test that's due today.
Yes, sir.
Do you need more time, or do you think you can take it tonight? Are you prepared to take it tonight?
I can take it tonight. Yes, sir.
Okay, as long as that's not a problem, I'll go ahead and do it. I just gotta evidently I made a new one, so I didn't think it would count anybody else's, but it was weird because I changed the name of it and then I imported the old a new one from another class that I had made, and I used the old one's name, and like the other one just disappeared. So I'm thinking that's what happened. It just merged it and it thinks you already did those. Hopefully it still has that score. But either way, I'm going to give you 3 more chances.
Okay, thank you. And
Okay.
then second thing, for the face-to-face exam, I also messaged you on that same message that I was prepared for it after
Mhm.
class on Tuesday, and you didn't reply to that. Again, I understand you were sick. Just wondering if I could get the code and do the mirror proctored
Yes.
version tonight.
Yes, you can do that. And what I'm going to do is I'll set this till 5 p.m. tomorrow. So that'll give you tonight and tomorrow.
Okay, thank you. I should be able to take it today. I just gotta drive home, and that should be an hour or so with traffic.
Okay. Thank you.
All right, thank you.
Bye
Have
bye.
a good
Sorry about
day.
that.
Oh, no, you're good. Thank you.
Anybody else there?
I just had a quick, I was wondering if you could post, I tried to find it from last semester, but I couldn't find it. If you could post the Excel that you normally use
Oh, gotcha.
for our
Yes.
grades. Just a little bit anxious about where my grade's at right now. So if I could
Yeah,
do some
I
some
get you.
hand calculating, that would help me.
That's on me. Yeah, let me, in fact, I thought I was already there. Let me double check.
Maybe I'm looking in the wrong spot. I was looking on and Canvas. I just didn't see it. So like maybe I'm
Helpful
looking at it wrong.
documents and links is where I normally put it. Let's see. Ah, 241, 242 course grades.
Oh, okay,
And
cool. I was looking at the wrong thing.
yeah, just
Perfect.
click on the percents to make sure they're matching. But I'm about 99% sure that I did update them for the new percentages on my syllabus.
Okay.
But it wouldn't hurt to check. But either way, it's going to be a good, accurate, a fairly accurate thing, even if it doesn't have the original percentages in it.
Okay, perfect. Thank you.
All right,
Have a
or
good
even if
one.
it does have them, I should say. Thanks, Carter. Have a good one.
You too.
Nice to see you out here, Marcus.
Yes, I came to ask a question about
Hmm.
the retake face-to-face stuff.
Right.
Right. I just wanted to know exactly how you wanted it. I just didn't want to do it and then be like, oh, dang, I did it wrong.
Right. So if you click on the assignment on your Canvas page, which is in the last weekly module or very close to the last weekly module, I tell you what, let me do this. I'm going to stop share and I'm going to share my screen. This one looks just like mine, just like the one in your class. So I'm going to share
Okay.
this screen instead and show you exactly what you're supposed to do. So right here, it says F2F test 01 redo. If you click
Hmm.
on that, this tells you exactly what you're supposed to do. It says open your lockdown browser and have your phone ready to take pictures of one or more questions and answers at a time. Once you have a photo of each problem and its answer choices, paste them into a Word document with very narrow margins. At the end of each question with its answer choices, insert spaces for you to insert a photo of your neatly done solution and then paste your solution here. Later, I tell you neatly done, see below. And if you go down below, you'll see how to neatly solve a physics problem. So that tells you everything you need to know right there, Marcus.
Okay, so it's the picture of the question, my work, and then and my work neatly done under it.
Yes. And then the next question, and then your
Oh,
work neatly done. And then the next question. Don't forget the answers have to be in there as well. And you want to read it because it tells you some stuff like you got to make sure you circle the right answers. You got to make sure you state the equation. You got to
right.
make sure you insert the numbers with the units, at least initially. So just read that over and highlight parts or print it out before you do it.
Okay, thank you.
You're welcome. Have a good one, Marcus. What's up, Mark? How can I help you, sir?
Yeah. Can you help me with a question in test one?
Yes. Yes.
It's problem number 21.
Okay. Can you pull that? Or do you have that? Or is this on face-to-face test one?
Yeah.
Okay. So let me go to there real quick. It'll probably be easiest if I just do it. Face-to-face test one. Hope
Yeah. I'm just.
the publishers don't get mad at me because I'm going to show it to you. I'm going to click on it first and then get it sort of centered in the spot. And you said it's the first face-to-face test, and it's which problem?
21.
21. Okay. Trying to shrink this down. There you go. All right. So now what I'm going to do is share
Mhm.
like that. And you're talking about that question, right?
Yeah.
All right. Let me copy this, some information down onto my iPad, and then I'll share my iPad to work it out.
Yeah. I tried to draw it out at first, but then I got a bit lost when drawing it. So.
Gotcha. Okay, you got this. What it says is an electric dipole with plus or minus 5 microcoulomb point charges is positioned so that the positive charge is 1 millimeter, 1.0 millimeter to the right of the origin. So I'm going to say this is positive 5.0 microcoulombs, and this distance from here to here is 1.0 millimeters. And the negative charge is at the origin. Okay, I did not expect that. That's negative 5.0 microcoulombs. Okay. And how much work does it take to bring the 3 microcoulomb charge from a point very far away to the point x equals 3 millimeters? So we want 3 millimeters. I'm going to put that right there. And y equals 0 millimeters. So it's literally this point right here, which I didn't draw to scale, but that's okay. So we want to know that's the point P. We want to bring a 3 microcoulomb charge. Okay. So what we can do is calculate the electric potential at that point, and then if you multiply the electric potential at that point by the charge that has, then that's supposed to give you the actual work required to bring it there. So it says the relationship between the electric potential energy PE, charge, and voltage delta V should help you answer the question, but you will need to calculate the electric potential V at the location of 3 microcoulombs due to the 2 charges of the dipole. So they're giving you a really big hint, but they didn't really give you the equation. The equation we're going to go for is, I'll write this way, say solution, and work is equal to the question mark, and that's bringing the 3 microcoulomb charge. I know I haven't shared the thing with you real quick, but I want to write down this stuff real quick. I've got that right. Okay, so let me kill this. I think I have everything I need. So I'm going to stop sharing that, and now I'm going to share my iPad screen.
All right.
Okay, so that's the picture I have. So what I'm going to say is this is just like the problem we did in class today. The voltage at P is equal to the voltage at P due to charge 1, which I'll just say is the positive charge, plus the voltage at P due to the negative charge. So this is going to be equal to, since we use V equals KQ over R, there's going to be a common factor of K in it. So I'm going to say 8.99 times 10 to the 9th newtons meter squared per coulomb squared. And then that's going to be times negative, no, I'm doing the positive first, so it's going to be times 5.0 times 10 to the negative 6 coulombs. And now the distance away is, in fact, remember the positive one is at the 1 millimeter mark and the point is at the 3 millimeter mark. So this should be 2.0 times 10 to the negative 3 meters. And then the next one, since it's a negative charge, I'm going to put minus, and then 5.0 times 10 to the negative 6 coulombs. And this one is, in fact, 3.0 times 10 to the negative 3 meters. And that should be the whole voltage, but the work will be equal to, let's call this guy Q. It's going to be Q times V at P. That should give it to us. Okay. So let's go ahead and calculate this. It looks like I'm going to take 5 times 10 to the 6 times 10 to the negative 6, that is, and divide it by 2 times 10 to the negative 3. That's 0.0025. And then I'm going to take negative 5 times 10 to the negative 6, and I'm going to divide it by 3 times 10 to the negative 3rd. And that's going to give me 0.001666. So I could add 2 extra sig figs if I wanted, and that would be that. So I'm going to take this number, the 0.0016, and add it to the 0.0025, and that gives me 0.00083333. Okay, that's the whole answer inside. Now I'm going to multiply that times 8.99 times 10 to the 9th. And that gives me 7.492 times 10 to the 10 to the 6th volts. So that's 7.492 million volts. And remember, a volt is a joule per coulomb. So now I can say that the work is going to be equal to 3. Whoa, Nelly. There it goes again. Work is going to be equal to Q times VP, which equals 3.0 times 10 to the negative 6 coulombs times 7.492 times 10 to the 6 volts. Actually, I want to write it this time as joules per coulomb, since we need to remember that. And when I do that, I'm going to say, whoa, no, okay. I just made I evidently hit my calculator with my arm or something that did something crazy. So 7.492 times 10 to the 6 times 3 times 10 to the negative 6. That's going to give me 22.47. Actually, that's times 0.48. I can make that an 8. Joules. So I'm thinking the answer should be about 24 joule or 22 joules, and 22.4. That's probably because I carried extra digits. They're calling that 23. So that's probably the right answer.
Okay, so 23. Yeah, like, so the part I was confused was I wasn't really sure what was supposed to be the negative charge number. So like, you say that the negative charge was negative 5.0 microcoulomb, and I didn't realize that we knew the number for the negative charge. So I think
Oh,
that's where I got messed up.
yeah. Remember with the voltage formula, specifically this one right here, unlike the electric field and the electric force, where I told you don't use the charges in there, in this equation, it's really critical that you use the charges, the positive and negative signs, in addition to the numbers. So if that's what you're talking about, then yeah, definitely make sure you check that out.
Yeah, okay. And one more question.
Uh-huh.
It's in test 2 and it's question 16. It was about if you were to cut a small ornament ball magnet in half, and
Uh-huh.
yeah, that's the question.
What question is it? 20.
Question 16 in test 2.
Okay. Oh, in test 2. Okay, let me get there. That's different now, isn't it?
Yeah, I said that one piece would be magnetic North Pole and the one other
Ah.
piece would be South Pole.
That might have been well, I mentioned this in class a couple times, but it's only something I said. It's nothing I ever wrote down, or wasn't related to any of the problems we did. But basically, when that's the fundamental idea of Maxwell's equations. One of Maxwell's equations, specifically as the state that we know of now 100 years in or whatever, basically we know that there's no such thing as a magnetic monopole. And what happens when you take a bar magnet and cut it in half is you get two whole magnets, a north and south on the left and a north and south on the right. And if you cut those halves, you get another bar magnet with a north and south, and another bar magnet with a north and south, like that. In fact, if you keep doing it smaller and smaller, you'll get to the point where there's no more domains big enough to have any significant magnification, so, or magnetization. So in that case, it will just not be a magnet. So you're never going to get a North Pole or a South Pole by itself. Now that
Okay.
I'm going to pull that open so you can see it though.
Then the answer would be each piece would in itself be a smaller bar magnet with both north and south poles then?
Yep.
Okay.
That sounds like it. I'm going to check it real quick, see if there's any other answers. Which number did you say it was? Number
16.
16? Okay. There it is. Okay, cool. So let me share this. Stop share. Share. Okay. If you were to cut a small permanent bar magnet in half, neither piece would be a magnet. Each piece would be in itself a smaller bar magnet with both north and south poles. One piece would be a magnetic north pole and the other piece would be a south pole. And none of the statements is true. Actually, this might be one where none of the statements is true, because as I explained to you, if you get small enough, then it just stops being a magnet. Like you can imagine if you were down to 2 atoms, what's the likelihood that you're going to get, cut one magnet and or still have a magnet made out of just two atoms. But let me check the answer for that real quick. So I can
Alright.
do this. Actually, I'm going to say keep editing this quiz. Let me stop sharing for just a second so I can pull up what I need to pull up. And then where'd I go? Where'd I go? Where'd I go? Where'd I go? Uh-oh. I think I have lost my window. Oh, there it is. Whew. Scared me. I forgot I'd made it so small it was hidden behind the other window and I couldn't find it anymore. Felt like an idiot. I was like, ooh. Okay, so I'm checking what it had for that question. It's a little easier to find when they're numbered, which they're not on my side. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Ah, here it is. Yeah, okay, so they weren't taking into account cutting it up so small. So yeah, it is, each piece would in itself be a small magnet. I just wanted to make sure they weren't splitting hairs there. That would be one of those ones that sometimes students might more accurately answer it than the question bank's supposed to. I would kind of argue for the other one to be answered, but I'm going to only take the answer that I told you there, which was that it makes two small magnets.
Make two small magnets. Okay, and I think that's my questions for all the test.
Okay.
Alright, so and you have Zoom tomorrow as well, right?
Yes. Yeah, I
Alright,
sent out. I assume you saw the email that I sent out?
I'm gonna check it right now.
Yeah, I sent it out about 4 o'clock. So it should you should be able to find it. All right.
Have a good day, Professor.
All right, you too. See you, bud. I saw you came back, Marcus. How can I help you, bud?
Yes, I did come back. The questions, it's for every question, right?
Yeah, you got to do all of them, not just the ones you missed.
Okay. That's pretty much all I wanted to ask. I just wanted to make sure before I started.
Yeah, you really want to take this as seriously as possible because this is your chance to really learn how to solve those problems. Because one of the things I could possibly do tomorrow, for instance, deliveries here, Shawnee, is I could, or say tomorrow, on the final exam, I could take a bunch of questions from those previous face-to-face tests and just write them with no multiple choice and maybe even change the numbers of it. And I would want you to be super successful in such a case. So if you actually use the time to learn how to solve them as opposed to just memorizing the answers, that would help you do better on a test, period, whether I do it that way or not. So definitely try to use this to your advantage because I don't care. God, my hat looks so stupid. Because I really don't care about the number of points I'm going to give you. I'm not going to put a whole lot of work into grading it to make sure I get an accurate assessment of the points I'm giving you. I'm probably going to err on the side of giving you all the points. But that's because it's up to you to be disciplined enough to make sure you do it. Okay.
Okay.
But I do have 3 office hours tomorrow, Saturday, and Sunday that I'm planning on holding. You can text me, that kind of stuff. So if you need help, let me know.
All right. Thank you very
All right.
much.
Have a good one, Marcus.
You too, and get better.
Thank you. You have a good day. Bye bye.